It's 8 o'clock, so we will be starting. Hi everyone, so welcome to the O-level last minute webinar. Yes, tomorrow is your physics paper 2. Okay, I hope that you're not nervous, and so that's why we're here today, right? Yes. So I'm going to share with you guys some of the very useful techniques like later. So if you remember and can use some of it, probably can help you pull out a few marks. So before that, let me do a short introduction. So my name is Claire. So I teach lower set science, O-level and A-level physics at OVERMUGGED. So something about myself, right? When I was a student, so I get straight A for my O-level subjects, and I also ace all my tests and exams. So basically, yes, I know how to actually score well. So when I become a tutor, right? So that's actually also what I focus on. So teach my student some of the techniques and some of the like very useful things you can do to help you improve your score. Okay, so some fun fact about myself. So I used to have photographic, I say used to have photographic memories when I was a kid. But then the thing is, it's not very useful. I can only use it to remember like lines from TV dramas. So when I grow up, this photographic memory is like gone. So yeah, I cannot really remember things. So I resort to like very how to say the dumbed down way of memorizing, repeating and repeating and repeating. Okay, so for tonight, right? So I'm not going to share with you like whatever the photographic memory or the dumb things. So we're just going to focus on a few very important things, how to memorize, and also what are some of the important key things you can remember and you can use probably tomorrow. Okay, so a little bit about Overmark. So for Overmark here, we have spread our passions for more than 10,000 students, and you can find us across the 7 branches in Singapore, and also, of course, you can find our presence in the different social medias. And we are so well loved by our students, of course, from our results from our students. So 70% of our students right actually achieve distinction. And then for myself, last year my Set 4 classes for both the O-level string and also the IP classes, half of them right actually improved from like failing or like just pass to getting an A1 for their O-levels and also for their end of year exams. And some of them actually just joined me for like 2, 3 months, really right before their exams. So I will really say that the things we do here, so some of the skills we share, which I'm going to share with you guys later, are very useful. So remember to use them tomorrow. Yep. So without further ado, let's start today's topic. So for today, I will be using the 2024 paper 2. Okay, yes, so this paper is from last year. Of course, you'll not be seeing like, not very likely that you'll be seeing exactly the same questions. But for physics, same as other subjects, you will seeing the same kinds of question, like the different parts, like come up again and again, like every few years. So what I'm going to focus on today, right, not like the specific parts of it, but rather some of the parts that will actually come out like again and again and again. So you remember the techniques, right? And you remember the phrasing. So that will be very useful for you to use actually tomorrow. Okay, so I'll be like just going through a few questions, but the rest of the paper, right, will be sharing in the Telegram channel again. But along the way, if you got any question, please let me know as well. So you can type in the chat. So later, at the end of the 1 hour, right, I'll also save some time, like for you to ask like any pressing question you want to clarify. But please don't ask me what is Newton's first law. I will say check the textbook. Yes. Okay, so the first question is on the kinematics. And okay, the first one will be fine, and this one here. Okay, so if you check these questions, right, the ball first hit the ground at the time t equal to 3 seconds with a speed 15 meter per second. So these are like the some of the important informations. So usually when you do the, or like tomorrow when you're doing the paper, right, you usually will read very fast. And trust me, 80% of students, they will miss out some key information. Then later either you are stuck or you forgot to mention the key information. So get this habit. Okay, learn it with me. When you read the question, right, take your pen, you just underline the important things. So like this one here, we have hit the ground, okay, and it's also first hit, not like the rebound. First hit the ground at 3 seconds, and the speed is 15 meter per second. Okay, explain how this value, okay, they ask you to explain, so these are keywords, and refer to these values. Show that air resistance acts on the ball as it falls. So also a little bit hint, usually for your O-level question are linked to the previous part. So if you can see previously, they actually ask you to state the acceleration, and then here, they ask you to explain it. So if I put it together, right, if I have a acceleration, if it's constant, can I just use it to calculate? Yes, I can, because I have the time. So you see, just now you underline, so now I can use it. If I have the acceleration, I have the time, it just like drop from rest. You see another key information from the front. It dropped from the rest, so that means u is equal to 0. I have my u, I have my t, I also have my acceleration. So actually I can calculate the speed when it hit the ground if we don't have air resistance. Using the formula, a equal to v minus u over t. So if I calculate it right, the speed should be 30 meter per second. But the value is only 15. So use the value 15 is lower, so I can deduce that because the acceleration is lower, so there is air resistance acting on the ball itself. So this is a question of like, okay, it's a straightforward, it's only a 2 mark, but how can you answer using the data? So that will be the challenging part. So the second challenging part about this question is the 4 mark, sketching the velocity time graph. And it's not a very straightforward, like no air resistance, so it's a straight line. It's actually a graph with air resistance, and it also involves 2 directions. When the ball is dropping, so if you visualize it, when the ball is first dropping, versus later when it hit the ground when the ball is going up. So when you sketch the graph, right, your graph should have 2 parts. When it's dropping, then the velocity should be in one direction, that's going down. Then later when going upwards, your velocity is going up. So it's in the upward directions. So if it's speed, everything is just a value. So there's no positive or negative. But if it's velocity, it's a vector. That's why the scale you see that they give you positive and negative. So in this case, if we take upwards as positive. So when the ball is going down, I should have a negative velocity. And then later, when the ball rebounds, we should have positive velocity throughout the whole thing. So I have a little box for you guys. Whenever you are sketching a velocity, displacement, time graph, always pay attention to 2 things. 1, the change. So is your velocity increasing, decreasing, or constant? Okay, so for this part, right, I know that it's dropped from rest, and then it reached a speed of 15 at 3 seconds. So if you start, I will start at 0, and then later at 3 seconds, I know that it will reach a speed of 15. And as we mentioned just now, right, since we take outwards as positive, as it hit the ground, you'll be having a downward velocity. Hence, the velocity will be negative 15 over here. Okay, so I know that, okay, my graph should be going down like that. So next, ask yourself, my gradient, is it increasing, decreasing, or constant? So then this part, you've got to actually link it. So if it's gradient of velocity time graph, then this gradient should be the, depending on the acceleration. And then acceleration, they'll need to know, then what affects my acceleration? F net equal to ma, my resultant force acting on the object. So the resultant force, then need to look at the forces acting on it. So hence I'm saying that this graph is not very straightforward. If without air resistance, free falling, there is only weight. Then the F net is just equal to the weight. So A will equal to G throughout. Then you have a very nice straight line. But if there is air resistance, right? So if I look at this, there is the weight, and then adding outwards, there's the air resistance. And the property about air resistance, right? If I'm going to add it here, your air resistance is proportional to V, or like V squared. Okay, but I'm just going to simplify it. Just say that it is proportional to V, meaning that the faster the speed, then the higher the air resistance. So at the beginning, right, it dropped from rest, the V is 0. So then the air resistance should be 0. So in this part here, my F net is just equal to the weight. But as it go down, the speed increase. So you can see that my A will start to increase. So then therefore, I will have a smaller F net. And I will have a smaller F net, a smaller acceleration. So my graph, my A is decreasing. So hence it will be a decreasing gradient. So I should draw a line that is getting less and less steep. So my line will look something like that. Getting less and less steep. So I would suggest, right, if you go by the upward, like the curve up, curve down and all that, it will be confusing sometimes. We have positive and negative. So instead, you can look at, I have decreasing acceleration, hence I have decreasing gradient. So my graph should get less steep. So again, decreasing gradient, that means that you'll get less steep. So that's why my curve should getting more and more gentle, meaning more flat. Okay, so after that, when you hit the ground, it will rebounce. Then rebounds, usually it will increase very fast. Then also the velocity right now become upwards, so it should reach positive values. So remember, here we're in the real world, so there will be some loss in the KE. So it rebounds, it will not be hitting 15. It should be somewhere lower. Okay, so we're looking at some point that's lower. And the question also tell you that the ball is in contact with the ground for 0.2 seconds. Sorry, I made a mistake just now. It should be at 3 here. So it's at 3, and then after 0.2 seconds, when it rebounds, it should be at about 3.2, somewhere in the middle. And as I say, right, the speed should be lower because you'll lose some of the kinetic energy. So then the value will be somewhere lower here. So I think let's put it about here. So this part, you can draw a straight line. So the velocity will change rapidly from a negative value to a positive value as the direction actually change when the ball actually rebound. Okay, then after that, it tells you that it actually at 5.0, the ball reached the highest point. So whenever, right, the object, if we throw it, we reach the highest point, let's say when it temporarily arrests. So at this highest point here, the V become 0. So at 5, we know that the velocity again should decrease to 0. So our shape will be somewhere like that already. Okay, from the maximum, then go down. So we know that, okay, it should be decreasing. Again, second point, we need to ask ourselves. So the gradient, the acceleration, hence the F net. What are the forces? So this time around, right, as it's going upwards, so weight is still adding down, but your A, instead of adding upwards, as a change in the velocity, it should be in the opposite direction. So my A actually will also be adding downwards. So the beginning here, at the beginning here, when it's going upwards, my acceleration, my air resistance now will change to be acting downwards. So my F net will actually be greater than the weight. The acceleration will be acting upwards. The acceleration is acting downwards because your F net equal to ma. So by your Newton's second law, right, your acceleration is always in the same direction as your F net. Yeah, this is also a very important concept to know that don't confuse your acceleration with your velocity. Your velocity, you can see here, you just follow the direction. Yeah, so ZY here has a question. Yes, we can also start with positive V. So it all depends on, you see, it all depends on how we define it. So which direction you take as positive. When this question never specified, right? Yeah, you can actually define your direction. So that which one is positive. Okay, so let's move on to this part here. So how should I draw the curve? If someone you know the answer, you know, can try it. So, well, our F net stays constant when going up. So the hint is that apply what you learned just now, right? Yes, Isabel has the answer. So you actually become less steep. Why it become less steep? As we said, the gradient again depends on the F net. But the F net is the sum of the weight and air resistance. Then air resistance affected by the speed. So as the speed actually decrease, right, the A actually will decrease until become 0. So at the highest point here, for our ball, it will only be the weight acting on it. So our curve, again, so become less steep. It's the steepest at the beginning, then after that, it become less and less steep. So again, it's a curved. It's a curve and has a decreasing gradient. Yeah. So the rest of this question I think will be fine. Yep. So for question 2, right? Okay, we're still on the forces. So I just want to highlight this point here. When you're writing for the action reaction path, so these are the 3 points. So again, you can find this in the PDF file. But this question I found is a very interesting because usually I will just draw the arrow as the driving force. But if you look at this case here, that actually tells you that this driving force is acting on the car than by the road itself. So when we are writing our action reaction pair, one of the key thing, right, to mention are the two bodies. The one that exerting and the one that the force is exerted on. And the question, actually they tell you the answer, like the body A and your body B. So you're going to mention that later, the reaction force, right, is since the road exert the driving force on the car, so the reaction force should be the car exert the reaction force on the road itself. So again, the other 2 points, the magnitude, so same also 5,000 Newton, and then the direction, so driving force to the right, so then this reaction force should be to the left. Okay, so I'll be moving on. So I'll be moving on to question 6, but along the way, right, you can take a look at your 2024 paper. If you have anything you're not sure, you can ask in the group, ask in the meeting chat as well. So you have time, then we'll actually go back to go through that later. So question 6. Okay. So question 6, right, we have a mixed question of our light, so the ray diagram, and then we also have echo. It's a bit interesting because it's actually using like normal, okay, we have a sound wave, but then it's actually reflecting. So it's actually an echo question. Okay, so let's take a look at the ray diagram first. So this is a mirror, this is a ray diagram for the mirror image. So as usual, right, we will actually draw the image first, and then we connect it. Okay, then we do the usual. But then this question, right, they actually give us the 2 incident ray first. Okay, that's a bit unusual. Mm. Okay, so that's a bit unusual. So then what should we do with this question now? So I would suggest, okay, there are 2 ways to do it. Okay, one, if you have your mat set and you are quite fast doing your construction, okay, then you can do this. Okay, take out your ruler. Okay, then from here you draw it. For the most method, right, first thing is always connect it to your mirror first. So make sure that your incident ray hit it over here. Okay, so once you have it ready, right? So the first method you can do with your projector, you can actually measure the angle incidence, and then you can quickly measure your angle of reflection. With the angle, right, then you can draw the ray. So you can draw for this one, and then you can also draw for the other one. After you draw the normal, so you can also do the same. So once we have the 2 reflected ray, right, so the point that we intersect, and then that's actually the location of the image. So that's actually for answer for our part 2. So alternatively, right, second method, we can go by our usual way. So the usual way, right, for mirror image, what to do is that, okay, since I have a object over here, right, so I draw the dotted line. Okay, so then I measure that this part here is, okay, I have 1.3. So I mean the other side should also be 1.3. So then we will have 2.6 over here. So then you can have a location. So by using the equal distance, the object and the image are equal distance from the mirror, I can locate already. So by drawing just a straight line, then equal distance, I can locate the image. So usually, right, we will draw like the ray, then let it hit the somewhere like here is the observer eyes. But this question, since they already give us the 2 incident ray, right? So make sure you connect it from the image to the point of incidence over here. So the other one also. Okay, so make sure they all come from the same point. So if you want to make it more complete, you can also label the I and the R, the I and the R. So this will be like a bit unusual for the ray diagram for the mirror. So when you're doing a bit like atypical questions, right? But you can still apply the concept that you have learned, the steps. But then you need to pay attention, look at the questions. Okay, I already have this. So my ray, right, the later it must pass through this point. So instead of like just drawing a random one, I should just connect my image to this point of incidence, and then I can draw the reflected ray. So similarly for the other one as well. So if you pay attention to the specimen paper, right, and also this year, that means last year's paper, you can see that the question nowadays compared to the previous year's one, right, is actually focused more on your application, which actually means that you need to really understand the questions, what they actually give you, and then you apply the relevant concept. So the relevant concept here is that all the reflected ray, right, when we extend it, they should all intersect at the position of the image. So if I already give you the tool, you should be able to connect it to draw at the image over here. Okay, so for part B here. So part B here we have a pulse of ultrasound used to detect the distance to targets, as shown here. So the time taken for the pulse to return is measured. So if you remember this method, right, basically if I measure the time, then we can times the speed. Then we have a distance. But because this is echo, so the distance is actually going to the target and come back. So for this to work, the question tells you that the reflected pulse, it must arrive at the sensor before the next pulse is emitted. So it means that the time, right, for it to go there and then come back can only be the time between the two pulses. So the time between the two pulses should be the period. So it means that to find the distance, right, actually we need to find the period first. And to find the period, so again, let's read the questions. So it tells you that the sensor, it actually emits 8 pulses per second. So the 8 pulses per second, so that's the frequency. And then my period, I can use a 1 over f to find the period. So the distance traveled, right, in this amount of time is 40 meters. And then again, because this is going to the target and come back. So the distance is only half. So 40 divided by 2, so that will be 20 meters. Okay. Okay, so Isabel has a question, so we can. Okay, so before we move on, right, Isabel also have a question. So in this method here, just now if we are using the angle, right, this one I would advise to use your projector to measure accurately rather than the estimate. Okay, why? Because like usually, right, in physics, if I'm using this method, that means the second method, I draw the position of I, then I draw this. So usually we don't need to measure the angle because it's already connected. Okay, but if you're using the first method, you are using the angle of reflection is equal to angle of incidence, right? In this case, you want to ensure that the angles are equal. So hence, I would advise to use your projector to make sure the angle are really equal. Yeah. Because I do hear from my student, like some of their teacher, when they mark their paper out, they have something similar. They really go and measure the angles. So the angles are not the same, then they will minus mark when they're using this method. Okay, then we also have another question for question 2. Sorry, I think it's question 3 here about the pressure. So why a small force applied at piston P is able to produce a large force at piston Q? Okay, so this is a hydraulic system. So in the hydraulic system, right, so one of the important concept, because liquids is incompressible. So when I apply a pressure here, the same pressure is transmitted at the other end. So that will actually be the first point we're going to talk about. Okay, as the same pressure is transmitted from piston P to piston Q in the confined liquid. So by using a larger area, so the two pressure is the same, right? As this side has a larger pressure, then F over A. a larger area will means that you also need to have a larger force. So in order to produce the same pressure. So by using a larger area at Q, so the force exerted will need to be larger in order to have the same pressure. So since you guys are here, I can also show you guys the answer for C part 1 and part 2. So these are some of the explanation questions as well. Okay, so we have another question. In the calculation, why I use 2SF rather than 3SF? Okay, so in the calculation, right, usually we'll follow the least SF. Okay, and then for physics, right, the number we use usually is 2 or 3. But this question a bit ambiguous, cause like if you see 5,000, you can look at it as 3 or 2. Also 3,500 can also look at it as 3 or as 2. So same as the other numbers. So therefore, I would say the final answer, you can do 2 or you can do 3SF. Yeah. So 2SF or 3SF should be accepted for this case. Okay, we have another questions for the bubble over here. Okay, so why there is more work done to crush the paper when the oil contains the bubbles? So again, right, if you look at how this machine works is that I apply a force over here, okay, it moved down. So there is actually work done by this force. Okay, then where does this work done go? It's used to actually lift out the piston and then the piston will then crush the waste paper. So if there are bubbles inside, right? So basically my energy, so again, starts here. The work done, some of them will need to use to compress the bubble. Okay, to compress the bubble first. So that means that I will have less energy left to be actually passed to our Q. This Q right now has less energy, right? It will do less work. So it's a bit like, okay, for the same amount of energy right now, I can only transfer lesser to them. So in order to do the same amount of work, then I need to do more over here. Okay, so another question for the laboring. So instead of say friction, right? Because the question actually lump it together as resistive force. So you should actually follow them. Because they say that the driving force and resistive force are the same. So these two will follow the first part. Then this one we just combine the normal contact force. Then the weight you can also say, yeah, gravitational force or attraction. Do we need to mention the magnitude of the forces? In the vector diagram, usually no need. But your length, right, should follow approximately. It means that you know that this driving force is larger, right? The arrow, you should draw it slightly longer than the resistive force. So since this one, we know the magnitude. The free body diagram, usually we don't need to draw the scale. It's not the scale vector diagram. So it's different things. So you don't need to label the scale. Okay, then let me see. There's one more question. So if we have 15.2 plus 15 equal to 21.2 or 21 for the list S. So it actually depends on the previous value, right? Actually, if it's okay, usually plus minus we follow DP. So in this case, here your 16, it doesn't have any decimal place. So follow the list DP. Then multiply divide, we follow the list SF. So that will be 2 or 3 SF. So most of the time, right, in physics, we are doing like multiply or divide based on the equation. So that's why it will be list SF. Okay, yeah. I would say that to be more precise, usually we'll do the follow the list SF. That's why some question will be 2 SF, some question will be 3 SF. But they also say that if you are very like, just like don't want to think about it already, so you just do everything 3 SF. At most it's to minus like that 1 or 2 marks in front. Yeah, so same to this question, okay, you just put everything 3 SF. If you put it at most, yes, you just like minus that 1 or 2 mark for the precision. But if you feel that that actually help you like save the mental load, like keep thinking the 2 SF or 3 SF, right? Too much thinking already, then you can just leave everything 3 SF. But sometimes you see the effort is just not justified the mark. Okay, so yep, let's move on. Yeah, I think I got one more question. So usually in practical, they will be more strict about this one. But then for the theory paper, right, like the overall, okay, there is usually like 1 or 2 marks for the overall SF. So it will not be like every question they will minus like 1 mark, 1 mark, 1 mark like that. It's like the overall, the whole paper. That's why some of the school teacher or like the student will just say that it's not worth the effort. Yeah, for theory paper. So for the very big values, right? Yeah, like this case here, you can just leave it in standard form. It's okay. But if it's standard form, right, so make sure your DP, like, don't write 8 times 10 to the power something, write 8.0. So you also write at least 2 SF. Okay? Okay, we shall move on. So after we finish with question 6. Okay, question 7, this one is a DC circuit question. So as a quick way of, whenever you look at this type of circuits, right, always identify the relationship. And one of the very easy way, right, is use your thumb to cover up. So let's say if I cover up over here, if I cover up this entire thing over here, right, you realize that now the current can flow through. So it means that this 100 ohm is in series with everything. But let's say if I cover up the 48, okay, the current cannot go through the 12. So this two is in series. But if I cover up the 30, there can still be current going through this way. So that shows that this branch and this branch is in parallel. So once you identify the relationship, right, then usually start combining with the most straightforward, meaning that you only have one kind of relationship, like these two. They are in series. Okay, so just add it up. So 48 plus 12. Then from here, I can see that, okay, this branch, if I add it up, this branch and the 30, they are in parallel. So combine the parallel first. So after that, this whole thing, if I combine them as one, if I look at them as one circuit, okay, imagine there's a block over here, and then this block and my 100, these two, they are in series. So after we combine this already, so the series, right, this one and this one is just adding together. So this will actually how you analyze it, how you analyze the circuit and how you do the combining. So after that, you can apply, if you want to find the potential difference across A and B, so since just now I already combined them, this is 20, and this 20 is in series with 100. So to find the potential difference, right, we can apply the potential divider rule. Mm. Okay, I have a request to go through the idea about potentiometer, like how by varying the length can vary the PD across it in the DC circuits. Okay, so for the potential divider, right, actually using the same formula as well. So the difference is that, okay, I'm going to draw the quick demos for this one. Okay, so imagine this wire, right, is a potential divider. So then if I'm only measuring the PD from here to over here. So basically, right, this is only the measuring the PD across these portions. So how is this? So if you're using the formula just now, if this entire thing has a total resistance of RT, and then this part has a resistance of R. So the PD across here, right, will equal to R over RT. times the overall PD. So this will be the first point we need to note. Second thing is that how do we link it to the length? Because here we are using a resistance wire. So for the resistance wire, right, okay, we'll assume 1 is the same material throughout. Okay, then 2, it should be uniform cross-sectional area. Okay, why I need to know about these two? Because whenever we look at a resistance wire, the resistance is affected by resistivity, length, and the cross-sectional area. So if resistivity and the A, right, is the same, then my R basically is directly proportional to the length. So hence, this ratio, right, the resistance here over the all resistance, we can actually change it to the ratio of the length. That's why by varying the length, right, basically I'm varying the resistance. And hence I change this ratio, and hence I change the PD across this part we are connecting. Okay, so we shall move on to the next part. So we have a current in the lamp, we have the power supplied. Okay, all these, most of them will be applying formulas. Yeah, so it's actually, and for part B, right, you can see that the answers actually are linked to each other. So once we find the PD across this junction, right, because the branches, they are connected in parallel. So that PD basically is the same as the PD across the two. So to find this current, we can do the PD across the total resistance. And then the power supplied to the 100 ohm. Since I find this PD already, so actually I can just do minus. So I can find the PD across the 100 ohm will be the other 7.5. And then after that, we can just apply formula. Use V square over R. So this one actually have more than one way to do it. So you may actually use other method to find it as well. Okay, question 8 is a bit on the database question. So again, some of the hard things to highlight, right? If the question actually give you a table and say that, okay, using the table, describe the effect. Okay, to be safe, don't just put like, oh, increasing, decreasing. Please quote the data. So you can describe that, okay, as a current increase from 8 to 40 ampere, the time taken for the fuse to melt actually shorten or like decreases from 10 seconds to 0.09. So that way, right, your answer not just like describing, but you also include the data from the table itself. That way will be definitely more complete. This part don't need because they only ask for the time to melt. So this part doesn't melt. So it's not really related. So the rest actually is using the information, applying it to answer the question already. Okay. I will go back a bit on the 7B part 3. Okay, 7B part 3. To find the power supplied to the 100 ohm resistor, right? Yeah. So to find the power, we need to, we first record the formula. So either I need to use V square over R, which means that I'll need the potential difference. Or the other way, right? I square R. Then you need the current. So you need to decide which one you want to do. So let's say if I want to use the V square over R, right, to find the potential difference. Okay, just now I already find the potential difference across here. So remember I said just now, right, your 100 and this whole thing here, basically they are connected in series. So in series, you split the potential difference. So this 9.0 volt basically is split among the 100 and this whole thing here. So this whole thing across AB, you take 1.5 volt. So therefore the 100, you will take, see, you will take 9.0 minus 1.5, you will take 7.5 volt. So that's the PD across the 100 ohm already. Oops. Then we can apply the formula already. So V square over R, hence the answer will be 0.5625. So then again, right, this one why I round to 2SF? Because the data here you see 9.0 is 2SF. So the rest here, right, although this can say is 3 lah, but the list is actually 2. That's why for this question, actually I round off to everything 2SF. Okay, I have a request for 8. Yeah, I can also use P equal to VI, but that means that you also need to do a second step to find the current. Yeah. So that's why usually if I already have the resistance, just apply this. So that will be like faster. Okay, let me see. Just now my request for question 8. Yeah, I lost the questions. Okay, the person who asked about question 8, can you message me again the question numbers? Okay, thank you. B part 2. Okay, so B part 2 here, right? Why the fuse cannot be used as a fast flow fuse? Okay, the fast flow fuse, right? It tells you something. It need to melt in less than 0.1 second. Okay, when the current when okay, the two conditions are at the current rating, the fuse does not melt. But when it's twice the rating, right? The standard one will melt in 1 second, but the fast flow will melt in 0.1. So if you go back to the table again, the one less than 0.1 is 40 ampere. So the 40 ampere is twice the rating. So that means that twice the rating should be at 20. But then if the rating is at 20, it cannot. Because supposedly at the rating, it shouldn't melt. But at 20, we know that it will melt within 0.35 seconds. Yeah, that's why it cannot be used as a fast flow. We're looking at the condition. Okay, so question 8 is part C. Okay, so part C here, the resistance of the wire in the fuse is 0.015. Okay, and very important, they say that it does not change with temperature. So when we have a current of 30 ampere and more, all the energy transfer is used to melt the fuse. And no energy is dissipated to the surrounding. So with 30 ampere, right, what's the energy transfer electrically? Okay, this one we got to calculate. So again, the power, okay, use the formula I square R. The current is 30, the resistance is 0.15. So you can find the power is 13.5. But to find energy, right, E equal to PT, I also need to have the time. Then go back to the table. So at 30 ampere, it takes 0.16. So this is actually the time taken for it to heat up enough energy to melt it. So then the energy it actually transfer in this whole thing will be the power 13.5 times 0.16. So it's 2.16. So again, use the least SF should be 2SF, 2.2 joule. So then for part 2, right? So how can I just do the minus? Because if we calculated in the amount of time that for it to melt, it should transfer 9.6. But from the previous part, if all the energy is used to melt it, actually I only need 2.2. So why there is a difference? So the difference, right, is this 7.44 is the energy dissipated to the surrounding. That's why for this working, we just need to find the difference. And hence we link it to the, part 3 and part 4. Okay, for part 3, convection through the air, then conduction must be in contact. That's why will be the ends of the wire. Then if we change to vacuum, right, we don't have air already. But for the 30 ampere, so there won't be any significant change because as the question mentioned, if it's 30 ampere and low and larger, all the energy you just use to melt it. So you don't really have energy dissipated to the surrounding. But for 8A, right, for 8 ampere, the time will be shorter because now means that less energy is dissipated. So less energy is lost. Okay, less energy is dissipated to the surrounding, which means I can actually save more energy. every seconds I have more energy used to melt it, and hence the time taken will be shorter. Usually we don't mention the wire to the air because your air will be considered a poor conductor. So that's why the solid part, right, the connection part, that one actually will be more energy loss due to conduction, whereas air is through the convection. Okay, if you do radiation, but your radiation does not require a medium, then you cannot mention the second part where each of the process occurred. So that's why I got to link it together. Yeah. So same question now, why we cannot talk about radiation? Like, yeah, it doesn't have really a place. It does not require a medium. Okay. So the term-wise, right, should use thermal energy rather than heat. Okay, in the current syllabus, usually we say energy is transferred by heating. So heat is used as a verb. So we don't say like heat energy. We can say thermal energy. Or to be safe, just say energy. For 30 ampere, no change because for 30 ampere, right, all the energy transfer you see is used to melt the fuse. So no energy is dissipated to the surrounding. So it doesn't matter like the surrounding is like a vacuum or anything, because the whole thing happens very fast. So you don't have like very little bit. Mm, okay, so will only be very little bit. Okay, I think for this part. Okay, I think I have a very interesting question here. So when some of the question asks you to pick the main thermal process, right? So why some of the question over the 2 years include conduction, even though it's air? Air, right, usually I would say that the main process actually should be convection. Because if it can flow, right, it will set out the convection current. Yeah. And then radiation will depends whether it's like a significant, does it contribute to a significant amount? Yeah. So hence you got to look at, that's why I think we need to look at the context of the question. So if you like like the sun, right, because there's like no medium. Hence the main process definitely will be radiation. But let's say that if I look at how is the energy, right, let's say transfer from this cup to the surrounding, that would say the main process, right, should be convection. Like I have a hot beverage. So that heat actually will be dissipated to the surrounding by convection. Mm. Okay, this one I just want to actually show you guys how should you answer this type of questions. Okay, for radioactivity for this type, the concept testing here is the penetrating power. So you should know that, okay, this is like the reference. So by right, you should have a total of 650. So every time when it's a drop, right, means that there is some radiation, like there's some particles being absorbed by this medium. So your job is identified. So it's paper, right? You should be able to identify that is alpha. And then if it's aluminium, the particle should be beta. So therefore from here, yes, there is a drop. So it shows that since the alpha particle can be stopped, so the drop actually shows that yes, it emit alpha. And then from 500 to 0, also there is a drop. So yes, it emit beta because beta can be absorbed. It can pass through the paper but be absorbed by the aluminium. Then how come there's no gamma? Because if there's gamma, right, aluminium cannot stop it. So then there should be some reading after the aluminium. So therefore, the 0 reading means that there is no gamma. Because if there's gamma, they will pass through to give you a reading. So tonight, actually, if you want to do the last minute marking, like memorizing all the definitions, all the key concept, right? Strongly advise memorize all your definitions like this type. What is it meant by background radiation? Describe the background. Okay. What is it meant by background radiation? State like this type. How do you do that? And also state what is it meant by half-life. Okay, how should you go by this? You can take a look at your TYS, the topical one or the yearly one. Best will be the topical one. So you take out the topical one, take out all the paper 2, look at all these like state, defined, all these are questions, then memorize the definition, everything again. So usually there will be like quite a substantial amount of marks allocated for this. And they are very strict in marking this type. Yes, you can use that as well. Okay, this one I just give you a more general, so you use a radiation detector. Okay. For your session B, so for this session, right, you only need to choose one question. So make sure you don't do both. So choose one question, and again, my advice, because quite a few number of my students, right, they look at one question, they see one part they don't know how to do, then they decide to do the other question. Then after they do the other question, they realize that it's very hard. So usually, right, don't just look at one part you don't know how to do. Look at the entire thing. Also look at the question. Should actually look at the number of marks that you are confident that you can do. So you see like which question that you have like more marks that you're confident. So like one question probably is like really 1 mark, like the whole part, 2 marks cannot do. But the rest like the 8 marks, actually it's quite easy to do it. So you should try it. Okay. Okay. So I can show you guys this part. So later I think you also refer to the PDF. So this is one of the question that came up quite often for the transformer. Why we should use a alternating current as an input current instead of a DC. So the reason is because of the AC will give you a changing magnetic field lines. This is linked to the secondary coil. So changing magnetic field line means changing magnetic flux, which can induce the voltage and the current in the secondary coil. So to pay attention that the phrasing we use here, right, is all the terms. So for Cambridge, right, when it comes to marking the qualitative describing explanation question, they are very particular about the correct terms used. So for EMI, electromagnetic induction, okay, they were definitely looking for terms like the changing magnetic field lines, then the linking, then your Faraday's law, the rate of change of magnetic flux or magnetic flux linkage. Then it induce the voltage and the current. Yeah, so be very, very careful about the terms you use. Okay, so for this graph, very flat and then very large on the other side. So these are the characteristics for the diode. And as you can see that for the negative, right, the current is super small. That's why we can like take it like the current is only in one direction. So this actually link it. So you cannot just use like the definition for diode. You are got to use your sketch. So the feature about our sketch is when the voltage is negative, the resistance is high, the current flow is negligible. So this is actually the one that you got to mention. Then you can talk about how is it ensure that the current only flow in one direction. Okay, so this is drawing, sketching the magnetic field lines for the solenoid. So again, right, for this type of question, so I will advise tonight, same thing, go back to your textbook, take a look at the common patterns they are testing for the syllabus practice drawing. So for solenoids, right, one of the things that you need to take note is that inside here, you can see the lines I'm drawing, actually it's all straight lines. So you can use ruler and you should use ruler to make sure it's all straight. Second thing, because the field inside is uniform, that's why the spacing, right, should try to make sure is about the same. So it's an equal spacing for the uniform field lines inside the solenoid. When do we say magnetic flux instead of magnetic flux linkage? Actually, for the O-level syllabus, right, I would say that we just use a magnetic flux linkage because that's actually stated in the Faraday's law. But because we didn't really like go into the details of what's the difference between the two, right? So sometimes in the marking, they will accept like both magnetic flux or magnetic flux linkage. I would say that Actually, anything you see got the turn, like the many coins, use magnetic flux linkage. Mm. And this question I think is a bit interesting because instead of like a normal circuit breaker, this thing is using we have the two solenoid. But the difference is that this one here, right, is connected to the live. And then this one here is connected to the neutral. And then the fault is when the live wire touch the metal casing. So this question is very interesting because actually instead of just testing on circuit breaker, they also test on the earth wire. So that's why the first point we got to know is that when you touch the earth wire, right, the current will flow through the earth wire to the ground. So there won't be any current flow through like the rest of the circuit and go back to the neutral. So meaning that the current here actually will become like almost zero. Should be zero. Okay, then this one here actually will become very large because your earth wire will have lesser resistance. So the current flow through the casing earth wire and also from the beginning here, the live wire, right? The current here will be very large. So as a result, the solenoid here will become much stronger and attract this part. So the solenoid here is stronger compared to this one. So the forces here is stronger. Hence, you will attract and cause it to rotate this way. So you rotate this way, then you will push up. So when you push up this part, then you break the contacts. So this is like a very good example of like, you not just demonstrate, cannot just like memorize and regurgitate. You got to really apply in the context of the questions. So if you have time later, you can take a look at how we actually phrase it, how we actually weave in the concept for the earth wire. I think you link it to the two solenoid thingy. Then talk about the implication for the forces and hence the rotation. Then the rotation then finally lead to the thing rotate and break the contact. Correct. 11 part A is using the right hand grip. So use the right hand grip. That's why you know that the north is on this side. The south is on this side. Okay, we have a bit of time. Okay, I only have one question about how sound is produced, like the sentence structure to explain the disturbance, the region of compression, and rarefaction. Okay, so if you want to talk about, so this is a point that in the syllabus, right, how sound wave is transmitted. Okay, let's remember first point, vibrating source, a vibrating source that create a disturbance. So this is the one that pushing the air back and forth. Second point, the longitudinal nature. Longitudinal nature meaning that the disturbance, meaning the oscillation, is parallel. So the back and forth is parallel to the direction of transmission of sound wave. Then the third point, hence this create the region of compression and rarefactions. So again, three parts. One, talk about the source of vibration, like the vibration, the vibrating source. So this one create a disturbance. Two, the longitudinal nature, how the vibration is parallel to the direction of the sound wave. Three, this create the region of compression and the rarefaction. When do I use interaction or magnetic field lines? When you want to talk about how they interact to produce a force. So this one usually is the the Fleming's left-hand rule. You talk about how they interact to produce a force. Sorry, this question a bit vague for the heat capacity, specific capacity. In general, heat capacity only need to care about the entire body, but where specific capacity is per unit mass. So one is for the whole object, like the pot, like the container. The other one is for the material, like water, like ice. Does the more conductor has more or less heat capacity? That one depends on a specific question already. Because this one looks like it's in the context of the question. We are not required to know about how is the material effect. How does ultrasound produce the image during the ultrasound scan? When it hits, right, the different tissue, it has a different rate, different amount. If you look at it, right, so some of them will reflect, where some of them can actually pass through. So then when you reflect, right, then you actually pick up the depth that is reflecting. So hence based on the depths. So meaning it's still using the echoing. So ultrasound scan, right, is still using the echoing. So based on the time, they can actually map out the depth and hence the silhouette of the organs inside. The heat loss or power dissipated. Okay, how to explain heat loss or power dissipated? Okay, are you referring to these questions, right? Okay, let me reply here. Referring to which topic? So you need to look at the specific topic to know about the phrasing. Would the velocity time graph negative? Is it wrong if positive, and why is a curve again? The velocity time graph, right, it should be one part positive, one part negative. Why? Because the ball, right, actually one part is going down, the other part is going up. So that's why to the two journey, right, the two velocity are in the opposite direction. So for vector, definitely one positive, one negative. And why is it a curve? Because the gradient is the acceleration, which depends on the net force. So the net force is affected by the amount of air resistance. So when it is dropping, so when it is falling down, right, as the speed increases, air resistance becomes stronger. So that's why the acceleration becomes weaker. Because right now, when it's dropping, the air resistance is kind of going up. So it kind of like help to hold up the accelerative force here. But then when it's going up, right, because now it's going up already, so air resistance act in the opposite direction, so it's acting downwards. So because of that, it acting downwards, two of them actually create a retarding force. So at the start, when the speed is the highest, it has the greatest retarding force, hence the highest acceleration. But as the speed decreases, right, the air resistance start to decrease. So it's like weaker already. So you have like lesser retarding force, hence lesser acceleration. For electrostatic charges question, do we use negative charges or positive charges or electrons and protons? Or it doesn't matter. I would say, right, usually we will say positive charges and negative charges. But when you look at the movement, please make sure, okay, very important, only negative charge will move. Because only your electrons can move. The positive cannot. It depends on whether it's okay. For electrostatic, do we say induce a negative charge or gain a negative charge? Induce, right, is by using induction, like the one that you see, remember using the rope, then the spear. That one is induce because it never touch. Induce means never touch, But when I say gain, right, it can be like touching, the conductor touching, then you transfer. Or like the rubbing, the friction one for the insulator. Then there's also a transfer. So for thermal energy, power dissipated for the DC circuits. So again, right, I would say that, okay, standardize it, right? You can say that the thermal energy transfer to the surrounding, okay, for the thermal energy, for thermal processes. So thermal energy transfer to the surrounding. So the heat loss is more like, okay, heat loss, heat gain, we're looking at the interaction with the surrounding. Yeah. Then whereas for power dissipated, right, this one is also referring, okay, for your DC, okay, they are looking at like if you have a device, they are using the energy from the source, correct? So that's why we say the energy dissipated or the power dissipated in the device itself. Yes, you can. Mm. Okay, I have a question. I think this one you can take a look at the answer key later. But basically, right, the transformer, like the power station, the cable, and then the final transformer, these three parts, they are in series. So the current, after you step up, right, it will be the same current as in the cable. That's why after we step up, the current in the cable is also lower. If you need to see any part of the question, right, the PDF will be shared in the channel later. Then what other background radiation is there rather than cosmic and radon? You have it on your food as well. So like potassium, you can have it in the bananas. So some bananas can be yeah, radioactive. Okay, so some of them are is in the present in the food because some of the isotope by nature is already radioactive. But like the radiation is super small. Okay. So I think any last minute tips, right? I would say tonight, before actually you go to bed and all that, actually should like I said, actually one of the things that you can do, right? Take a look at your topical TYS and take a look at all the definition question. If you're the kind that not very good at those, right? Go and memorize the correct ones from your textbook or from your school's notes. Yeah, so make sure you can score for those. Okay. Okay, so before we end off, so for those you are like really locking in for your O level, then after that, score very well and go to JC. Just like a head start that your O level actually, yes, it's tough, but then when you reach your JC, right, it's a whole new thing. So when I was like recording, right, when you're studying for your O level, right, the amount of content you have, we are comparing in the JC context, roughly that's the amount of stuff you need to learn in half a year. So whatever things you're going through right now, like memorizing the stuff for the past 2 years, you will be only like doing it and revising it like for half a year. So that's why for the entire JC syllabus, right, it's going to be much like heavier and more difficult by both like the quantity and also the difficulty level. So therefore, we are here for you. Yes, and this is actually what our students say about joining us for our JC classes. So actually some of the students, they regret like not joining us like earlier. Like this year, my JC physics student, one of the guys actually improved from failing, like constantly failing to right now. He only joined me for the past, not very long, I think 2 or 3 months. Yeah, after his WA2, yes. And then for his promo, right, from failing to now is a very solid B. So it's definitely a very huge jump when you have the right amount of help. Definitely it's like similar to what you see tonight, not just about like going through the content like again and again, because most of the time actually you have it in school already. But what makes us different here is that can I actually help you understand it in a clearer way, especially for physics. Then after that, can I help you identify what is the method, the most effective and the time-saving method? Because if you 1 minute or 2 minutes save in solving your thing right, it means that 1 or 2 minutes extra for you to figure out the more difficult question. So hence, if you are ready and yep, you can actually join us like next year for the JC one. So while the rest is still like deciding whether they should go for tuition or the honeymoon period or like think that they can figure things out and then they start to failing things, then they feel that they need tuition, that is a bit late cause need to not just attend the lesson but also need to do catch up. So if you already have like the early head start, that will actually be to your advantage. Especially it's the same 2 years, but you're basically doing like 2 times the content and more difficult as well. So that's why I would say get all the help you need. Okay, so if any question, you can head over to the Telegram channel. So as we said, the PDF, right, will be uploaded with the annotation that we did just now. Then if you have any question, right, I'm also in the channel. So yeah, I may also answer some of the questions. So yep. If you liked what we have tonight, so then leave us a Google review. Otherwise, like that will be all for tonight.